Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. In the last lecture of ECE2026, Introduction to Signal Processing, we introduced Z-transforms as a method for analyzing infinite impulse response filters. We previously looked at using Z-transforms to analyze finite impulse response filters. In this lecture, we'll introduce the idea of deconvolution. Suppose you have an image that's been subject to some kind of blurring. Maybe it's motion blur, or maybe the image is out of focus. In any case, we would ideally like to be able to apply some kind of filter to the blurry image to restore the original image. Now, this is a tricky process. You'll never be able to do this exactly, but if you're lucky, you can get close. Now, in the rest of the lecture, we'll look at one-dimensional signals. These images are two-dimensional signals, but the same underlying ideas will still apply. I'm not sure why the fonts are showing up strangely, and I feel too lazy to fix them. Anyway, this star here represents convolution. SN represents the original signal we would like to reconstruct, and XN is the result of the measurement process. So H of 1 here might represent the impulse response of a blurring operation, but the idea is quite general. What we would like to do is to take the measured data XN and pass it through a filter with impulse response H2 that we design to create an output YN, which is hopefully close to the desired signal SN. So ideally, if we wanted SN and YN to be the same, then this entire system in the middle, this cascade, which we can model as H1 convolved with H2, that should be a delta function. Because if you convolve something with a delta function, you get the same thing back. Instead of something like motion blur, suppose that our corrupting system H1 had an impulse response of delta n minus a delta n minus 1. So if a was equal to 1, this would be a first difference operation. And suppose we want to undo that. Now, I could take this H1 of n and plug it into this equation here, and say, okay, we'll solve this convolution equation. That would be extremely difficult to attack head-on. But remember that convolution in the time domain corresponds to multiplication in the z domain, and the delta function, delta of n in the time domain, corresponds to just 1 in the z-transform domain. So I can design H2 by setting it equal to 1 over H1. Now, the z-transform of delta n minus a delta n minus 1 is 1 minus a z to the minus 1. So if I think about what 1 over that is, well, that is the system function of an infinite impulse response filter. So to undo an FIR filter, I need an IIR filter. So here, this power of minus 1 indicates both taking a reciprocal and it indicates an inverse operation. So considering the example we just looked at for the particular case of a equals 0.8, we see that the original corrupting filter had this impulse response. This is a finite impulse response. And the recovery filter has this infinite impulse response. Now, this example is theoretical. Practical deconvolution problems can be fairly tricky. In particular, if your measurements are subject to noise, that noise can get accentuated by your reconstruction filter. Many practical deconvolution algorithms involve nonlinear signal processing, often using iterative algorithms. These are well beyond the scope of this class, but I would encourage you to explore them on your own. And actually, my own research career largely got started with this kind of stuff. My earliest refereed journal publications involved algorithms for deconvolving Hubble Space Telescope images.